It's been a pleasure to attend this meeting. My name is Shambhu. I am from Stanford and SLAC, and this is a tutorial. I know it's been the real talk marathon, and it's the second day, right? And so this tutorial is, I promise you, it is nice and easy, and it's the time to stay back and relax. Okay. So this is my team. On the top panel are my in-house collaborators, a long time collaborator David Rees, Tony Hines, and more recently Feng Lu. These three people are the real individuals who did most of the work, postdocs, and also two of them are leaving, Yuki Kobayashi and Denisa Bekashuba. They already left to start their new groups. On the bottom is it's my pleasure to collaborate with lots of people in different areas, like preparing samples and in theory and all that good stuff. Okay, here's the outline of my talk. I will take advantage of the nice the lecture that we had at the evening of yesterday. Mark did really nice on introducing the attoscience science, particularly the high harmonic generation in atomic and molecular systems. I start from there, just briefly remind you guys some of that aspects, and I will main part of my tutorial is to introduce you to the solid state high harmonic generation. I will tell you about the first experiments and the subsequent progress on understanding the microscopic dynamics leading to high harmonic generation. I will tell you about how these processes could be sensitive to solid state properties like Berry curvature and topological properties and things like that. And toward the end of the tutorial, if there is time, and I'll give my perspective on what the outlook of this field would look like. Okay, so this is just a reminder of the the experimental setup, a typical experimental setup where you produce high harmonics from atomic gas targets. So as we heard yesterday, this was first observed in the late 80s, right? And many of you either did some experiments like this in your career, or some of your colleagues did. This is my setup when I was a PhD student, and these are really nice harmonic spectrum. Since the experimental discovery in the late 80s, there was a lot of work, as we also heard yesterday, about understanding the microscopic mechanism of this high harmonic generation process in atomic and molecular systems. And this is the famous semi-classical three-step model, and that is able to explain much of the experimental observation. We can zoom into these three steps just a little bit to get some ideas of what level of the sensitivity that we are talking about. In the first step of this, this is the tunneling step right here. This is the Coulomb barrier that has been suppressed significantly by this laser field, and therefore the electron can tunnel out through this already suppressed barrier. This electron gets in the vacuum, and essentially when the fields, the electric field turns around, then the electron also has to turn around and come back, right? And with some probability, it could come back to the exact same place that it started from and find the parent ion. And when that happens, all the energy that this electron has acquired from this acceleration has to go somewhere, right? Because the parent ion is relatively heavy; it doesn't move. The electron, has to give up this energy, and that comes out in the form of this high frequency radiation, and this occurs, every half cycle and all that. So what you observe in the experiment is this interference of this emission. You typically use multi-cycle laser pulses, and these emissions they interfere, and what you observe in the spectrometer is this discrete harmonic peaks as a result of this interference. And this the harmonic spectrum, because they are essentially the train of attosecond pulses, and it was nice first attosecond pulse measurement that we also talked about yesterday, which is showing basically the train of the attosecond pulses in the time domain. Now, in many applications, you would like to have, instead of the train of attosecond pulses, you would like to have a isolated single attosecond pulse, so you can do a controlled pump probe experiment. This was my effort when I was a first-year graduate student to try to come up with a scheme which is now known as the polarization gating that many of you might be familiar with. And this was very near and dear to me because this was my first experiment during my PhD. And the basic idea here was that these driven electron recollision processes that they occur every half cycle of the laser field, you do some polarization, you provide some time-dependent polarization to the driving pulse, and in a way that now you have a left circularly polarized laser pulse at the leading edge and the right circularly polarized pulse at the trailing edge, and therefore with the known thickness of these wave plates, you can tune the delay between these left and right circular polarization, and therefore you have a range, a very small range, where you effectively have the linear polarization because the other projection cancels out, and therefore you have this small window where the laser is essentially linearly polarized, and everywhere else it is elliptical. So when the electron comes back, right, only here in this small region, you can find the parent ion and therefore produce one isolated attosecond burst. And as a result, right now you turn off the emission from the most of the pulse, because when it comes back, and now because of the elliptical field, so it's going to miss the parent ion, and most of the other emissions are turned off. And as a result, what you observe in the experiment is that instead of the discrete harmonic peaks that we saw earlier, we measure this supercontinuum. So that is the indication of the the really short gate that is about the half cycle of the laser field. So this is just one example that I wanted to give. There's lots of activities, as you know, in the field to produce shortest attosecond pulses, and there are other ways to get to this type of really short other methods besides polarization gating. The another aspect is the ability to probe the target itself. This is another pioneering work where Attoscience and others, they showed that by aligning a simple diatomic molecule like nitrogen, when you align this molecule, you use a laser pulse first to align the molecule, and then you come in with another pulse to produce harmonics. And you measure the harmonics as a function of this alignment of the molecule. And because these molecules have interesting geometrical shape, the harmonic emission is strongly dependent on this alignment. And you use this information, right? These are the harmonic emission for this various alignment angles. And using this information, they were able to retrieve the geometrical shape of the participating electronic orbital. So this, there's lots of approximation. Also was one of the controversial subject for some time. Nevertheless, this started the field, and there has been a lot of subsequent work, where you use this recollision, this coherent recollision process to image the shape, geometrical shape of the molecule itself. And you may ask, there is some time that, after the electron is launched, right, and gets accelerated and it came back. So within that time, if there was some dynamics on the target itself, you could also probe that. So this is another, really inspiring work from ETS group that, for example, in this molecule, when you started at certain time, like 0 femtosecond, there was some whole density in one side of the molecule, and over the time, this whole density moved to the other side of the molecule and came back. So if there was any dynamics that is going on in the target molecule itself, depending on if you know the exact return time of the electron, you have the ability to probe the dynamics of the evolving molecule. So as sort of shown here, right? So you can take advantage of the different wavelength of the driving laser. For example, when you go from 800 nanometer to 1300 nanometer, you have a knob. The wavelength has a knob to increase this return window of the time, and you can look at the various harmonic orders. They have different emission times as they are shown schematically here, and this is one way to probe the dynamics of this source molecule. So because of a lot of these interesting activities in the AMO, ultra-fast AMO physics, I was really interested to extend these ideas at the time to condensed matter system. And at the time, the way I thought about solids, subjected to a strong laser field was just like this. It is basically, a periodic array of, densely packed atoms, and there is a dressing field very similar to this, as you see in the case of single atom. Of course, the real solid is very different, right? And as we also heard yesterday, historically, this really the first nonlinear optics experiment that Peter Franken produced the second harmonics using the quartz, and in this plot, the actual dot is here. So this is the submitted copy of the manuscript that before the editors started to mess around, and there is that dot. This experiment is also was really near and dear to me because when I was looking for my postdoc opportunities, that was the building that I ended up to. So it was the exact same building, Randall Hall at University of Michigan. Especially the same place, but about 50 years later. So it was a very bad pump probe experiment that I had the spatial overlap, but very far on the temporal overlap. Because the solids are it's typically complex, so there are two approaches. One is you work with your theory colleagues to get predictions. The another approach is you just try the experiment. So I took the second approach. I took this mid-infrared laser system and took the zinc oxide crystal. There are several reasons on why that it was this combinations, but essentially the way to describe this is we did a lot of high harmonic experiments in like argon atom, right? Argon has 15 eV of ionization potential, and we typically use 1.5 eV of laser, and there's that ratio of the 10, like IP over laser photon energy, right? So one of the reasons here also at the time I thought, why didn't I get the same ratio so I get into the same, strong field regime, right? So zinc oxide has a 3.2 eV of band gap, and the laser is 0.3 eV, and I get this ratio 10. So we tried this experiment, and sure enough, without too much struggle, we were able to see these nice high harmonics. We observed up to like 25th harmonic order with relatively small amount of laser intensities. So as you note here, 10 to the 12 watt per centimeter square is a modest peak intensity. right, for this audience. I mean, in the gas phase, we use like 10 to the 14 type of watt per centimeter square type of intensities. And this is the crystal orientation dependence of the harmonics. There was one thing that was very different. Our reviewers at the time, probably one of you, pointed to this this high energy cutoff measurement. It was really wonderful to do that, and we found out that this scaling was actually very different from what it is in the gas phase. In the gas phase, you scale linearly to the intensity. Here we find it's actually linear to the field. So it suggested a fundamentally different, mechanism, leading to the generation of harmonics. And also, nature physics was kind enough to highlight our results, and I think Nina is probably here representing nature physics. We're really pleased, given that the PRL removed the dot, right? Since then, there has been a lot of exciting work by many groups in the field. And now I would like to walk you through these different mechanisms. They lead to generation of high harmonics in solids. Before I do that, I need to orient everybody, from something that we all know, which is this three-step model in the real space in atomic systems, because we need to go to the momentum space. So first, let me transfer you to the momentum space, just the atomic case into the momentum space. Now I see you, Nina. You're on this side. Okay, so here. This is what you see on your right is the momentum space description of this exact three-step model. You have this ground state, the parent ion is pretty flat, right? And you tunnel from the parent ion, this ground state, to this continuum. And this continuum is parabolic because it's a driven free electron in the vacuum, right? Strong field approximation. Once the electron is left, doesn't see the Coulomb potential. And then at some point, this electron can recombine to the parent ion, and this difference energy comes out. So it's basically the same thing, but in the momentum space. So this becomes useful in solids. So this was my version of solid before I actually self-taught myself solid state physics. And this is after some teaching, you have this. This is a very simple description of a solid, just using two simple bands. This is the valence band that has some dispersion now, right? It's not flat anymore. Similarly, this is the conduction band. It's not parabolic anymore. It has some curvatures, additional components to it, which basically represents the effects from this nearest neighbors and next nearest neighbors, and depending on the type of solid, you have different types of dispersion. Now, as soon as you draw this, you can see there is one type of possibility, which is basically because of this non-parabolic bands, the driven electron in the non-parabolic band could radiate high harmonics, and that's your channel A, let's say, what is now known as the intraband current, intraband emission. The other is this channel B, which is very similar to the gas phase. Essentially, it has this three steps that we talked about, and we'll talk this in more detail in later slides. This is the interband polarization that is very similar to the what we know in the gas phase. Okay, so the same thing again. I just wanted to put everything in one slide. In this case, so this is the three. These are the three steps. The tunneling. Let me just go here. So first of all, typically in semiconductors, you have the valence band is completely occupied. The conduction band is empty. So when you do the strong field excitation, you tunnel the electron tunnels from the valence band to the conduction band, leaving behind the hole, right? That's the step one. And in the step two, these both electron and hole gets accelerated in their respective bands. And finally, in step three, they coherently recombine. And this difference energy of the electron and hole in these two bands, it gives rise to this, high harmonic photon, right? Those are the three steps. Now let me go back. Ooh, I wish our it goes back. All right, so here again. So so this if you had the electron driven here on this band without recombination, right? So without the recombination, you could also emit high harmonics. So this is what I meant by this channel A. This could be potentially the part of the battle later between this interband and the intraband. I know there has been a lot of I guess lots of activities in the field. Every other nature or science paper fighting over interband and intraband. It's very important, but I don't think it's important enough to kill each other. Because there's things are already coupled, in especially in solids. So so this is one example of how this type of dynamics could probe the solid state properties. Okay, so here as we outlined this even in the first paper, and if we had a slight differences in the conduction band, for example, as shown here. So here this is just the semi-classical calculations. So if you had small changes, slightly different shape in the conduction band, and if you are just looking at the emission, the block, the intraband emission of harmonics, and you could see something completely different. So this is the these are two harmonic spectra. This blue, this green curve is for this green corresponding conduction band, and this blue curve is for the corresponding blue. I mean, they are different by a very small amount, but in the harmonic spectra, you see a big difference. So this is the strength of the nonlinear, process that if you know how to exploit, it's very sensitive. And there has been a lot of follow-up work. For example, the really nice work from Guliamakis, that came out in 2015. Essentially, in the different material in quartz, probing the different Fourier components of the band through this intraband current. Okay, so this we already went over this, but now the basic idea of this interband channel like this, right? So here, so in this step 3, you would emit this. But if you were able to measure the emission time of these harmonics, so if when the electron was being driven from this time 0 to T1, T2, and such, so the recombination at these different times would also give the high harmonic photon, but of the lower photon energy, right? Because of the lower momentum dependent band gap, between this valence and conduction band. So if you had a way to measure these emission phases of this, let's call these, different harmonics, then you have a way to probe this momentum dependent band gap in materials. So probing momentum dependent band gap is also not a trivial thing, even in the condensed matter physics community, especially when the conduction bands are unoccupied. Okay, so there has been some attempt to try to do that. This is nice work from Brabeck and Julio and others, where they use the same zinc oxide crystal and use this two-color method, to measure the emission phase of harmonics, and were able to retrieve at least some features of the zinc oxide band structure. So this is just the example of how I just gave two examples of based on this generation mechanism, the strength is to be able to probe the band structure, the momentum dependent band gap, and if I have time, I will show you some results on also you can probe the Berry curvature and topology of the materials. Okay, so now what is really we wanted to understand the similarities and differences between the this gas phase and condensed phase systems, and we chose this solid argon as in we thought it would be a really interesting system because the way these rare gas solids are formed, you basically have a very a pretty lousy system. This is the van der Waals solids. The atoms they have the completely filled outer shells, right? Argon atoms. So when you bring them together, they just they don't talk to each other. They just sit just sit around. So this we thought this would be a perfect system because there is it would be a good comparison because there is not so much interaction between these atoms, and also you can do the experiments where without changing laser parameters you go from gas phase to the solid phase, right? Which you cannot do in zinc oxide, at least not easily. Okay, so this is how we came out with the sample. It's a pretty pretty nice. Basically, what you see here is the growth of solid argon indicated by this Newton's ring on a really thin silicon nitride that is over the silicon mesh. Okay, so you essentially have like 10-20 micrometer thick solid argon. Within about 10-20 minutes you start to grow. Okay, so and this is the spectrum. Harmonic spectrum, pretty raw spectrum without doing anything. So the remarkable thing was that when we switch between the gas and solid, we just only switch the target, and we see that from the gas, the high energy cutoff is at around this place, like around 27th harmonic for that particular intensity. What we see, this completely new feature like the secondary plateau that is present only in the case of solid. So when we go back and forth between solid and gas, so solid produces this secondary plateau that in the gas phase we haven't seen before. This is the plot of the high energy cutoff as a function of the laser intensity, and this is the gas phase, pretty straight, right? And the solid, this is for the solid argon here, and this is for solid krypton. So we did argon and krypton, and xenon was too expensive even for us. So these are the this intensity locations where you have this first you have this fairly complex scaling, and then you hit this peak intensities, and where this is where you exactly at this peak intensity you abruptly see all these harmonics of the second plateau. They appear at at the instantaneous intensity. Okay, and that is true in both rare gas solids. And this this secondary plateau at the time was understood by including these additional labels, like instead of just two labels or two bands, if you like, if you add the additional like higher lying band, you can produce this secondary plateau. This is the nice work that we did together with the Metagard. Okay, so there's and since then there has been a lot of activities in the field in the theoretical side. So semiconductor block equation approach has been one of them, as we heard both the advantage and critics of this method this morning, right? I just wanted to point out just a couple of things here. This is the the momentum dependent band gap. This is the what we talked about, the T2 in the morning, the dephasing time between these two bands, and that is what we talked about. This is the Berry curvature, so I guess I just wanted to show you these equations. You don't need to go through everything, but just get this idea that this is what we measure, right? The intensity of the harmonics, which is typically the combination of the intraband and interband, emissions. But these parameters are there. So if you can actually go back with the help of a theory and analyze, there is the potential that you could probe. You have the sensitivity to this really interesting, solid state properties such as the Berry curvature. Okay, so I will maybe give a quick example on this Berry curvature. So this is the also the first time observation of the harmonics, high order harmonics from a single layer, single layer MOS2. So this is MOS2 is, if you're not familiar, it is kind of like graphene. When you get graphene, you peel, right, a layer of carbon from graphite, basically from pencil. So this is kind of similar. You peel out MOS2, a layer of MOS2 from the bulk MOS2. And when you do that in the MOS2, it is actually quite remarkable. The bulk of the material has the inversion symmetry as shown here. This is what we mean by this neutral. So this MOS2, molybdenum and sulfur are as shown here. When you have enough number of layers, this is the mirror plane. Okay, in the what's known as this AB stacking, and this is the mirror plane, and therefore you have only odd order harmonics in the spectrum. But when you peel out just one, single layer, as shown here, there are orientations where you break the inversion symmetry. For example, in this orientation, in addition to these odd harmonics, you measure both, even and odd order harmonics. And this was, just this itself wasn't really surprising that, people have produced a second harmonic from this system, right, for some time already. What was surprising was that the polarization of this even order harmonics were actually orthogonal to the drive laser field. So this, never happened, right, in atomic systems and arguably in molecules that, we talked about yesterday. So here is pretty remarkable that these even orders, they also have this, six-fold orientation dependence, but on top of that, the harmonics, the even orders are polarized perpendicular to the laser field. So what could give this, this orthogonal polarization to the harmonics? So, so there is some reminiscence of this, Hall effect, if you like. So where, right, you measure, you apply the electric field and magnetic field, and you measure the Hall voltage in the perpendicular direction. So in using that analogy, in the material, if you had, the driven electron in the conduction band of the material, so usually this is the group velocity. This is the, just the standard group velocity that everybody knows. And there is another term that is not so well known, that has this cross term with the Berry curvature, very similar to this, in this case, the, what the magnetic field does to the, driven current. So this usually, because the applied electric field is relatively small, so people don't really talk about this contribution, contribution from this second term. But in our case, the applied field is significant, that this term becomes comparable to this normal group velocity term, and kind of similar to what would happen to this driven electron if there was an artificial magnetic field, right? So there would be an anomalous current which is in the perpendicular direction to this normal current, and that would radiate the harmonics with the polarization perpendicular to the driving field. So this is, in that sense, this is the optical analog of something like this, what is known in the condensed matter physics community. So if you take this idea and if you build on these ideas, you potentially have a way to probe the various quantum processes through this all optical method in some interesting materials. You could do a polarization resolve measurement and get the handle on the Berry curvature, for example, and several groups have actually done that since this work. Okay, so this was sort of a progress report until this was David and I wrote this sort of as a decadal report, about 10 years from the first experiment. So Nature Physics was also kind enough to invite us. And this was this is the list so far as of 2019. And here we plotted the available, like the pump laser in terms of the photon energy of the laser. And this is the high energy cutoff, because if you're starting a new group, you kind of want to know, right, what type of laser you want to buy and what type of materials you want to, you can probe with it. So if you just take a look at this, for relatively large band gap materials, like, these circles are to represent the band gap. For relatively large band gap materials like magnesium oxide, the quartz, solid argon and such, you typically can work with the standard Tie-Sapphire laser 1.5 eV. And for smaller band gap systems like semiconductors, zinc oxide, silicon, MOS2, and graphene and topological insulators, which is not here on this plot. And as I said, there has been a lot of activities since 2019, and maybe there's a time, maybe now is the time to write another review, and I will talk to Nina afterward about that. So now for the rest of my lecture, I will give you some ideas on where the field sort of could be headed, how we can breeze the out in between this our ultra fast AMO, like attosecond community, how we can breeze to this other side, right, the other side of which is the material science, and whether this tool is going to be interesting enough, whether the material science community will also be interested to use this technique for interesting applications. So one of the things that is probably going to be a big deal in the next several years is to probe moire pattern. So these moire patterns are very interesting, which you form just by taking two sheets of graphene and orienting them at some angles, right? And similarly, if you do this in TMDCs, you can even form, as people have already shown, in interesting topological states and superconducting states. So this is their big deal, at least in material science communities, and now what our attosecond science community could offer is possibly a way to an all optical way to probe moire pattern. Okay, we haven't done that, so what we have done so far is we wanted to just see when you stack these different layers, what happens to the harmonic spectrum, not at a specific angle, but just on top of each other at a fixed angle. So this is what we see when we stack these like exactly on top of each other in this AAA configuration, which means that all these atoms are basically lined up like molybdenum and sulfur just on top of each other, right? So just to make it clear, this is the natural configuration. Naturally on this system, you have this alternate layers. They are rotated by 60 degrees. So this molybdenum goes to this place, right? So this is in the natural configuration. So when we take every single layer, we peel out and basically rotate them by 60 degrees and put them together. And this is the artificial, now if you like, is the AAA configuration. And we measure the harmonic intensity as a function of this number of layers. And you see this nice quadratic increase in the harmonic intensity as a function of number of layers. Okay, this is how so far we have done. And you can do this microscopy, like use the harmonics to probe the special property, just to look at the structure of the the target itself. For example, if you have 2-layer or 4 layers and so on, you can distinguish this by using harmonics. So this is potentially a next big deal in several coming years. The another big deal could be to probe the electron-electron correlations. So this is one example experiment. Here we have this again the 2D crystal MOS2. We pre-pump this MOS, the resonant weak resonant excitation, and we basically come in with the mid-IR, strong mid-IR driver and produce high harmonics. Okay, and we look at the harmonic signal as a function of this this photodoping. The basic idea is shown here. So if you did not have doping, you have this. Let's stick to one of the mechanisms. If it is the interband mechanism, then this driven polarization between this electron and hole, right? It's gonna give rise to these harmonics. But if you disrupt this coherence by putting extra carriers on the conduction band, then what we observe is that the harmonic signal reduces. Okay, so basically, this experiment was indicating that when you introduce more carriers in the conduction band, you increase this electron-electron interactions, and you subsequently kill the coherence between this driven electron and hole, and that gives rise to this decrease. Not only just the decrease in harmonic intensity, but also there is a harmonic order dependence on this decrease. So we did some relatively simple theoretical simulations where we were able to use this harmonic order dependent decrease to probe to at least get the estimate on this T2. This is not the absolute measurement of T2, but a relative measurement of T2. And what is shown here is that when you increase the number of electrons in the conduction band, you decrease the signal. You basically increase the dephasing. Okay, so this is one direction, one possible direction. The other direction is to probe the topological properties of materials. So this is there are several questions that I wanted to first outline. What are really the optical signatures of these topologically protected states, right? This morning we heard about the emission from this the ring currents and the emission from you have this high conversion from this topologically non-trivial states and orders of magnitude low emission from the topologically trivial states and things like that. What is really the signature of the topologically protected surface, and especially if you are an experimentalist doing this nonlinear optical measurements, you don't a lot of time you can't really trust on the peak intensity, and therefore just having high or low signal isn't quite enough. Because a lot of time you can't really do relative measurements. So you need some robust signature of these topological states. And also, how do you actually separate the contributions from the between you have to go through the surface first, right? And how do you separate the contributions from the surface and the bulk? But if you can get around that, then you have something equivalent to what we as a community we have been able to do in molecules, right? We could extend these ideas to condensed matter systems. And there's some really nice work from Denitsa and more recently from Christian from our group on these topological systems. So this is the theory. Again, here I just wanted to say that this is a relatively simple theory where we basically start from the tight binding model, And we choose like 2 bands. They correspond to the surface states, 2 valence and conduction bands. So this is the Dirac point, and a pair of the valence and conduction bands. So this is bismuth selenide, and we go through these semiconductor block equations, a very standard approach now, right? And then we finally sum up this intraband and intraband contributions, and we have the calculated harmonic spectrum. Okay, so as I said earlier, one of the challenges is to separate the contribution from the surface, right? So at least in this material system, so this is the crystal structure of the bismuth selenide. It is also layered material, very similar to MOS2 in that sense. If you just look at the top layer, which is shown here at the inset, there are some orientations where you break the inversion symmetry. Only on the top layer, only on the surface. So the bulk, very similar to MOS2, has recovers the inversion symmetry. So in that sense, the emission from the bulk, right? This is the emission from the bulk, has only odd order harmonics. But emission from the surface has both even and odd order harmonics. And what was interesting to also see is that the polarization of these even orders are actually quite quite remarkable. Because it depends on their polarization depends on the crystal orientation. Particularly when the laser is along this gamma to K direction, the even harmonics, they flip their polarization from the, here they were along the laser field, and here they switch to perpendicular direction. So just by rotating the laser field 30 degrees, all the even harmonics, they switch their polarization from along the laser field to perpendicular. This is quite remarkable. Okay, so this is what we predicted in theory, and this is also exactly what we measure experimentally. But let me first show you what we think is could be the robust signal of the topological states. Not really just the observation of these even order harmonics, because even on the broken inversion symmetric systems, right? If the surface has the broken inversion symmetry, it may not have the non-trivial topology, but you still you observe you produce the even order harmonic. So that's not the signature. So what could be the signature is this. So what you're seeing here is this. This is the Dirac point, the valence and conduction band of the surface state. This is the transition dipole moment that is plotted here, and you can see this pretty strange, this singularity essentially here at the zone center. And these ridge-like structures here, so they, so you could, these vortex features, they give rise to this, remarkable enhancement, for the circular field. Okay, when you drive the harmonic generation process, only on the surface states. So let me walk you through this plot. So here, this is the calculation results. The open diamond, these are the harmonic intensity as a function of the ellipticity from the bulk. Okay, bulk doesn't have this vortex feature because there is a band gap. The bulk has the band gap. So the response from the bulk is very similar to the atomic response, where when you introduce ellipticity, you basically kill harmonics, and for circular polarization, there is no harmonic emission from the bulk. From the surface states, there is for left and right circular polarization, the signal actually grows significantly, as compared to the linear polarization. This is what we observe experimentally. Okay, so in the experiment, we took a really thin bismuth selenide crystal and changed the polarization, and we find out that when you have a linear polarization, you actually have the smallest signal, and you increase the ellipticity, and when the polarization becomes circular, you have the most signal. So this is qualitatively different, right? Let me fast forward to my final results. So here we're not comparing just the different in intensity of the trivial and non-trivial states for linear polarization. So we are basically, here. Okay, so let me walk you through this. So this is the plot, typical, intensity plot of harmonics as a function of the ellipticity. So when you have, enough peak strength on the laser field, you have the emission that is maximum at the circular polarization. Okay. And here we plot the ratio of the emission for the circular polarization with respect to the linear polarization. And when we do that, we go through this material, bismuth selenide, and we also do something to the material itself. Okay. So when the material is pristine, you have this, as you can see from ARPA's measurement, this nice Dirac cone corresponding to this non-trivial surface state. And our collaborators add some indium, which has a smaller spin orbit coupling, so that reduces this band inversion, right? Essentially kills these surface states. So with for example, with 20% impurities, the surface state is completely gone. So we check the same material systems and do harmonics, harmonics generation, and we plot the ratio of the circular to the linear field, the harmonic intensity, and you can see, as you increase the doping, right, and there is a pretty nice phase transition going from this non-trivial to trivial phase, as shown from this harmonic response. This is probably more obvious plot. So this is, this is the topologically trivial state. Very similar to the harmonics that you get from atomic systems. The signal goes down as you increase the ellipticity. And this is the response from the non-trivial state, like two extremes. So this, this is the emission from the pristine non-trivial surface state. And that is the response from this trivial material. Basically, there is no surface state you can see through ARPAs. So my argument here is that we have this qualitatively different, not only quantitatively. Of course, the harmonic intensity for from the non-trivial state is more than 8 times higher. But we don't really rely on that because we may not know the absolute intensity of the laser. But this qualitative, qualitatively different intensity for the polarization is I think is pretty robust. And in terms of the experimental setup, they are pretty straightforward. In the reflection, also this this approach works. If you have a thick substrate you can't go through, then you can work in the reflection. And this is my final slide. So I was just wanted to give my perspective on how this field would evolve. So as you know, we started from like around 90s, high harmonics, and this recollision physics really kicked in. And we, as a community, we had a lot of exciting work, to probe these molecular systems, right, to produce isolated attosecond pulses. At around 2010, we produced observed harmonics from solid materials for the first time. And since then, there has been a lot of activities, and more recently, many groups are focusing on these 2D crystals and topological insulators and some interesting material systems that are, are part of this quantum craze that is going on right now. And eventually, we would be able to, with the help of the theory, be able to, do what's known as this Floquet engineering. Basically, when you have a really strong laser field and some interesting materials, when you combine these two, there's a lot of things that you can do. A lot of things that you can produce, like engineer this new material states. And ARPA's really, has been the workhorse on probing the band structure and all that, but it actually fails spectacularly when there is a strong field, just because the strong electric field, it spoils the electron that you produce from the surface state. And the harmonics, on the other hand, naturally, right? So we have the optical radiation that is coming out from the driven system, and would be a nice way to probe this. So with that, I will end here. And I would be happy to take any questions.
Well, thank you very much for this nice tutorial. So questions? Yes. Kind of triggered by your comment on flow-K engineering. So I don't know if you could expand a little bit what you have in mind, because I mean, to reach that regime, I guess we want to go for a combined laser system that is stressed, like with a very long pulse, from steady state, and then you want to probe that one with harmonics, or? Yeah, let me elaborate. So what is shown here is from Angel Rubio's group's work. So if you have this, oil material, for example, you come in with the circular polarization, a strong circularly polarized field, and you can make this this oil cone non-degenerate, because and now you have this. It's because of this circular polarization, you can make these two cones, they separated. And then you can, depending on the strength of the laser field, you can even, drive these cones in the Berlin zone as they show, right? So that's just one example. The other, there's a nice work from Michele's group and others where they argued that when you combine these interesting waveforms of the strong fields to materials like, boron nitride, and some pretty relatively lousy materials where there is no topologically, interesting states to start with. But when you combine these with, strong optical fields, you actually, potentially create these new topological states, right? So to be able to probe those non-equilibrium states, if you have the harmonics that you produce from there, and if you had a way to link the harmonic emission to these new topological states, so that would be, just a couple of examples of flow-K engineering. Yeah.
You started your talk talking about polarization gating. Okay, now if you think about solid states, and I prefer to think in terms of not Bloch, but rather Wannier Bloch picture, because then I start like in the atom with the localized or quasi-localized electron, which creates electron hole, goes up and recombines, but of course it can recombine in other place. So the polarization gating will not work there. Is there any studies about this mechanism, because they could lead to new physics also?
Yeah, so actually, we did an experiment in the magnesium oxide crystal, and we basically looked at the polarization response, right? And the circular polarization also produces harmonics, as we expected in that sense. So yes, so even in this semi-classical picture, you can rescatter from the nearest neighbor. And perhaps not as efficiently as if you are rescattering from the same site, but the circular polarization, even in systems like magnesium oxide, doesn't need to be topologically non-trivial, and so that's one of the remarkable differences. That yes, unfortunately polarization gating would not work, but I think I'm pretty happy with the circular field being a way to probe the topological surface states, because this is more efficient for the circular field.
Yeah, so you highlighted in your graph, the review graph, the relationship between the wavelength that we're driving the harmonics with and the band gap and cutoff. But I was wondering whether you think there are any other influences on the efficiency of the high harmonic generation from solids other than those two, kind of the ratio between those two, because from a lab perspective, some solids just work beautifully, and then sometimes you put something that should be similar band gap and it doesn't seem to produce as many photons. Okay, so that's really good question. So I think the answer is we should really forget about the strong field approximation. So let me elaborate what do I mean by that. In the strong field approximation, right, you mostly in the gas phase, the efficiency doesn't really depend on the target, right? So you go from argon to neon, and there is some ionization potential difference, but overall the efficiency is in the same order of magnitude. But in the solids, you go from one class of materials to another class of material. You have a completely new scenario.
for example, when you go from this, wide bandgap dielectric to topological systems, right, you have a completely new material system. In the condensed matter physics community, when they change materials from one, material system to the other, they expect completely different things, right? So that's what I mean by forgetting the strong field approximation, that this is fully materials dependent process, especially the class of materials. When you go from this wide bandgap dielectric to something that doesn't have any bandgap, right? How do you define these scaling parameters when the bandgap is 0, right? But within the same class, you could consider comparing, let's say, magnesium oxide and quartz, for example, because they have relatively similar bandgap, right? And there are some small differences. For example, quartz is much more efficient than magnesium oxide, and so on. So my suggestion is that when you go from one class of materials to a completely new class, you expect something different, some remarkably different things.
So I think we should move on. So let's thank Shambhu again.
Thank you.
Theoretical physicists and one is experimental. And I asked them before the battle how they would like to be introduced. And they send me a sentence each, so I will just read it to you. So we have Javier, and he's a last year PhD student at Quantum Information Group at ICFO in Barcelona. And he will talk about numerics in high harmonic generation. Then we have Stefano. He's a Marie Curie postdoc fellow at Aarhus University. And he simulates strong field dynamics in solids, probe big transient spectroscopy. Then we have Francisco. He conducts his theoretical research in high harmonic generation solids in the group of Dieter Bauer in Rostock. Then it's Kasia. She's our experimental physicist, and she's a PhD student in Imperial College in London. And she does experiments in strong field dynamics, in particular in solid high harmonic generation in wide bandgap dielectrics, which are close to damage threshold. So let's see where they take us in this battle today. Please.
Thank you.
Thank you.
So maybe at the beginning, we will want to have some of the contributions of you guys to the talk. So we chose a different strategy. It's a Mentimeter. So we have two ways. You either can scan the QR code. Anyone online watching as well can do that. So either scan a QR code, or you can go to menti.com and put that thing. And there is a first question there, just to survey the room, how many theory versus experiments we have here. Very easy, just so I feel a bit better that I'm not alone, maybe, or way worse. So there will be the QR code will be popping out throughout the talk when the question change, but you don't have to rescan it every time. If you just have it open on your phone, that's enough.
All right, so let's start. And so we decided to start this battle by introducing what we mean by the Attoscience of Solids and what we're interested in, right? And why it's interesting to look into the Attoscience of Solids. And what we all are looking at is the strong field control, strong field dynamics in solids. Why doing this? Well, because over the past decade, a growing number of experiments have looked into the strong field manipulation. Where is it? Is this right? No, it's this. Okay, sure. Into the strong field manipulation of solids in order to control, with these very short intense pump pulses, the dynamics, the electronic dynamics in solids. And this could enable faster electronic devices, optoelectronic devices, much faster than what is currently possible, going up to petahertz optoelectronics. And a series of strong field phenomena have been observed, including Zener tunneling, Van der Star localization, Franz-Gerlich effect, to name a few. This is one set of applications, but then, well, as we just heard, HAG has also been realized in solids, and this has become over the past decade a very good platform for high harmonic spectroscopy of solids, but also potentially a new source for high frequency radiation sources. And of course, whenever you are controlling the dynamics, electronic dynamics in solids with intense pump pulses, you're inducing a rich combination of intraband and interband dynamics. And in order to control, these strong field dynamics, then you want to have tools, spectroscopy tools that allow you to disentangle these effects, to really look at these effects in real time. And this will be the main topic of the battle. Someone is an experimentalist, others are theorists, and we use different techniques. We also look at different spectroscopy methods in order to look at these strong field dynamics. And we want to discuss about this also with you to see what the pros and cons of different techniques are, also what different theory methods you should use in order to model these dynamics. And this is basically what we are going to discuss. Of course, this is based on what we do. And so, for example, when we talk about the methods that we look at, well, this is what we work on. And so this is what we are now going to present, and this is what we are going to debate about. High harmonic generation and ATOS, at the second transient absorption spectroscopy. So we want to know you better. We are not going to show the answers now. This is more to start the discussion at the end. And so this is mostly to know you and who we are dealing with. What do you use in your experiments or in your theory? Are you more for HAG, ATOS? And now, well, you'll hear what we do.
Okay, so regarding this question, I think my preference goes to high harmonic generation, although I think ATOS can provide very nice insights.
Yes.
And okay, so as you already know, high harmonic generation consists in a process where a strong laser field interacts with a given system, in our case, a solid state system. And this leads to the radiation of high order harmonics that, as we showed, it has been shown in the tutorial, it can be, the frequencies that are generated can be either even or odd harmonics of the input driving field, and this depends on as we have seen, in the polarization of the laser field and also on the symmetry of the material. And also, okay, this resembles very much to some extent what we have in atoms, but there are some very interesting differences as it has been presented. For example, the linear scaling of the cutoff with the laser field strength, but also a reduced dependence of the ellipticity or of the harmonic yield with the ellipticity. Also, from a more practical point of view, there are some other differences. For example, in typical semiconductors, we work with mid-infrared frequencies. And on the other hand, there is also a very natural lower upper bound on the field strength that we can use, which is imposed by the damage threshold of the material. Also, there are some other differences, as for example, we can generate harmonics on transmission and also upon reflection.
Yeah, so as the only experimentalist, I will try to bring the theorists down to earth during that debate a little bit. So we usually like to think about and present our experiments just working and quite simple, but as we know, it's never as simple as just putting a laser into something. So there's quite a few different experimental kind of consideration that we have to take into account when we're trying to reproduce any results, but also even when comparing papers within the field, there is sometimes a lack of kind of very detailed description of something as simple as, for example, how intensity was defined and things like that. So I think whenever we talk about attoscience in solids, it's important to remember that there's a lot of macroscopic effects when we talk about the experiments.
So, okay, from the previous slide, one can get a bit afraid because there are a lot of things that have to be taken into account in order to have high harmonic generation processes in solids. But also, from the theory side, I think for most, for very simple materials at least, the dynamics behind are typically well known. So, as we have seen, there are the intraband dynamics and interband dynamics. The intraband are the ones related to Bloch oscillations. The electron oscillates, and therefore this oscillation generates a current. And the interband are more related to the three-step mechanism that has been discussed previously. Regarding these two, in theory, it has been seen that typically to the non-perturbative part of the spectrum, the interband mechanism dominates, while in the non-perturbative regime for lower energies, both of them, we cannot claim the dominance of one above the other. This doesn't mean that interband dynamics dominate over intraband dynamics, and in particular in this paper over there, this paper, they showed that when one theoretically takes out the intraband dynamics, then no harmonic efficiency is generated. Basically, the dashed lines here. And also from an experimental perspective, also it's very difficult to be able to distinguish from the intraband and interband processes. But maybe Attas can give an insight here.
Yes. So this is about HAG. Then we also heard in the previous tutorial about all the applications of HAG for strong field dynamics in solids, for accessing strong field dynamics in solids. But we also heard yesterday about the usefulness of absorption spectroscopy, especially X-ray spectroscopy in the talk of John Marangos. So why using Attas for accessing solids, for example? Well, what do you do in Attas? The idea here is basically to scan the strong field dynamics induced now by an intense pulse exciting a certain solid with an attosecond propulse, XUV or even X-ray. And by varying the delay, by varying the arrival time of this attosecond pulse, you are basically observing the dynamics induced by the intense pump pulse at different times. And then what you measure is the absorption of the transmitted propulse at different time delays and the variation in the absorption features. Now, this pulse is very short, therefore very broadband. And what you're looking is at how different frequencies in these very broadband pulse are differently absorbed at different time delays. And these variations in the absorption spectrum as a function of time delay give information about the strong field dynamics in the presence of the intense pump pulse. Now, why doing this? What are the features and advantages of Attas? Well, on the one hand, by using this very short propulse, you have extremely high temporal resolution. Then, since the pulse is short and broadband, you have simultaneous access to a very broad set of valence and conduction band states. You can see them simultaneously. And then by using an XUV or X-ray probe, well, you are directly exciting some core states. And as we heard yesterday, core states have the advantage that core electrons are bound to a given atom. And then by directly exciting a core electron, you are going to excite something that is localized in a certain area in your solid. And so by doing that, you know that you will have somehow state-specific access to, electron dynamics in a given point in your solid. And this gives you also sensitivity to the local chemical environment. And this is something that you can do with, X-ray spectroscopy that, you would hardly get with HAG. Now, we've heard before and also in the previous tutorial about this competition between interband and intraband dynamics. And this really led to a very intense debate at the beginning of, HAG in solids. Can you do something about that with Attas, for example? And I'd like to point to this paper by the group of Ursula Keller in Zurich. In this paper, what they observed was, so they used here this gallium arsenide, and they excited it with a pump pulse that was tuned to the gap. And therefore, you would expect that the main contribution here is interband dynamics, right? You are tuned to the resonance. But then with this combination of theory and experiment, these are theory results, but in very good agreement with the experimental results shown in the paper. Now with theory, you can basically distinguish, you can disentangle the two contributions and look, for example, contribution coming from intra and inter, and you see how these oscillating features as a function of time delay, they come basically from intraband dynamics, and you can barely, reproduce them with interband dynamics, which is surprising, right? You would expect that interband dynamics in this case would dominate. And this is something that you can do with Attas. You can, with theory and calculations, you can basically distinguish between inter and intraband dynamics, in this case. This is not the only case. Attas has been used to look at different systems and different solids, from dielectrics, semiconductors, semi-metals, transition metal oxides. This is from a review paper from the group of Steve Leone. It is showing some of, some examples of, systems that have been looked with Attas in different regimes also of excitation here. And I personally think that you can learn a lot with Attas in solids. Attas has been used for a long time in atoms, molecules. Also, the manipulation of the line shape has been recognized as a very powerful tool to learn about strong field dynamics in gases. And And I think that there is potential, a lot of potential, as also these experiments show, in order to make Attos as well into a real, analytical technique to access these strong field dynamics. This is at least my position. We'd like to know your opinion as well. Now, there isn't a poll on this, but there's something that we'd like to discuss with you also at the end of the talk. Especially what are the key challenges that we still need to address to make Attos into a real analytical technique?
Yeah, so we will try to now give like a very quick overview because there were so many talks about it before. So we'll give a quick overview of different applications of how high harmonics and Attos are used to study those solids. And again, there is a poll there if you want to say what you're interested in studying, what you kind of would want us to discuss more at the end as well. So obviously, we've probably all seen this kind of static measurement with high harmonic generation when they're able to reproduce, the different groups were able to reproduce this real lattice kind of periodic potential of our crystals, and that has been done in multiple samples, and this is kind of a well-established technique. And as mentioned before as well, high harmonics and solids were done before by different groups to kind of used as a very sensitive probe to the band structure of the solids, which Sham already mentioned is a very kind of useful tool, especially to kind of in the unprobed and which others cannot reach.
Okay. So a very interesting application from my point of view is that of Attoscience of Solids is that of ultrafast spectroscopy of strongly correlated materials. And okay, strongly correlated materials in a nutshell are materials that when we introduce very extreme conditions on it, it shows novel phases of matter with exotic features. And I think this is interesting because it allows a very nice mapping between quantum Attoscience of Solids and applications of quantum information science. I mean, there are a lot of platforms in quantum information science that actually need from these strongly correlated materials, and one of the main examples is that of quantum computing based on superconducting quantum qubits, superconducting materials. And I think Attoscience of Solids can help a lot on this because it allows us to study these materials, and this is shown in a lot of papers. So in particular in this one, what they did is to theoretically study a 1D Fermi-Hubbard model, an optically driven phase transition in this system. And actually what they show is that with high harmonic generation, they can basically distinguish the phase transition in the sub-femtosecond scale. And actually this is something that was also shown in 1D Bose-Hubbard models, with the main difference that now instead of having from the practical point of view, it's more difficult because you don't have an electric field that you used to probe. And also from a theory and also experimental perspective, a very nice work is this one about the study of phase transitions in high-density superconductors, where they basically used high harmonic generation in order to distinguish between different phases in a superconducting material. And okay, so as a wrap up, what I think is that high harmonic generation has a lot of potential towards quantum technology, and in particular, ultrafast spectroscopy of strongly correlated materials is a very nice application of it.
So before Stefano tried to convince you that Attos is the only way to kind of study time result stuff, our community, high harmonics and solids, have been moving towards looking at some kind of dynamical systems and some dynamics within solids. So here I just pulled out two recent, 2 years old papers where they were actually looking at the different the evolution of the high harmonic spectrum with time, where either they were probing the solid with a different pulse to kind of start this phase transition. And even though maybe yet we're not on the timescales that are possible in some of the Attos experiments, there have been kind of results here showing the time result, high harmonic generation. And also the high harmonics themselves could be used as a probe of different dynamics within solids. So as in the second paper, they were looking at how the harmonics themselves get changed and evolved with time over quite a long time scale as the kind of the topological states are cleaved with time because of the intense laser pulse. So
All right. Okay, but what can we do that you cannot? So for example, right, with HAG, if you want to induce HAG, then you need necessarily a sufficiently intense pulse. So you cannot really look at how, you know, your strong field dynamics or your dynamics, electronic dynamics in the solid, depend on the intensity of the pulse used. You necessarily need sufficiently high intensities, whereas with ATAS you can go from low to higher intensities. You really have this intensity dependence that you just don't have access to with HAG. And then the second thing, as I already mentioned before, you have this state selectivity that you get by tuning your XUV or even soft X-ray probe pulse to different cores. You can change the color of your X-ray pulse and tune it to different core states in the solid. And with this, you can access, you get state selectivity and sensitivity to the local chemical environment, as shown, for example, in this paper from the group of Jens Biegert.
So all these applications are really nice, and actually they are possible because there has been an agreement between theory and experiment. But there are a lot of points where theory and experiment do not actually agree, and also there are some debates within theory itself. So in the following, this is what we are going to discuss. So we are going to talk about suitable pictures for describing high harmonic generation processes in solids, but also how they could affect the numerics. And from a theory experimental side, we will talk about the phasing and propagation processes, how do they affect in the harmonic generation in the harmonic spectra. All of this with the nice background of ATAS. So now we are going to start with the part related to more theory, related to simulations. And in this case, we want to know what kind of simulation methods are you using? And then we can debate at the end, why do you have this preference? Okay.
Thank you. So I will just give a quick overview of 3 of the more standard methods which are used. There are many more, but there are also the methods which we will talk about today. So the story will start with the full many-body Schrödinger equation for all the electrons and nuclei in the solid, which of course it's impossible to do, right? Yeah, so you can come and start reducing the complexity of this Hamiltonian. So on the left, you have the electronic part, so the kinetic part, the interaction with the laser, then the interaction among the electrons, and also the electrons with the ions, and on the right sum and the right term, the motion of the ions, and also the interaction among themselves and the interaction with the laser. But yeah, you can bring this Hamiltonian to the single active electron picture by either neglecting some interactions or averaging them away. So you can start by neglecting or averaging the interaction among the nuclei. Also, you can neglect the motion of the nuclei at all, and then you can also either average or remove the interaction among the electrons. And in the case of the interaction of the electrons with the nuclei or the ions, you can also define some effective interaction with the background of ions, and then you get to the single active electron picture, which is widely used, right, at the beginning, and today it's still used. And yeah, and there are some other ingredients that you need to consider when solving either the TDSC or in the other methods. So you need to choose the gauge in which you are working. You can work either in real or momentum space, as Shambhu mentioned earlier. Also, you can choose when you expand in the basis of states, you can choose either a Bloch or a Vanier basis, or both, right? Or static or adiabatic states. Then you have to choose well, you can choose a different polarization or different characteristics for your of the field, like the spectral components, or you can define delays, and also the characteristics of your field can be such that you can neglect all the spatial dependence, and you end up on the dipole approximation. And then we have the semiconductor Bloch equations. So they are based on a more like a density matrix formulation of the Schrödinger equation. So for that, for instance, the most typical way to introduce the semiconductor Bloch equations is with an adiabatic expansion of the wave function. With this, you build your density matrix, and then you input that on the Liouville equation, and you get some equations of motion for these coefficients. And at this point, this equation that you see here is completely equivalent to the single active electron TDSC, but the semiconductor Bloch equations also imply including two additional parameters, which are two relaxation times. One is named T1, which describes the decay of the population of the states, and the other one is T2, which deals with the decay of the coherencies, right? And they input the equations as you can see here at the bottom. So the top equation is for interband, and the bottom equations is for intraband dynamics. And as you see, this T2 is more related to interband processes, and this T1 is related to intraband processes. And usually, depending on the applications, this T1 is in many time situations neglected, and this T2, this phasing time, will have different time scales depending on which states are you analyzing. So in the case of Stefano, for instance, he analyzes core states, while usually in high HHD you only care about more like valence electrons. Well, then the last method that I want to briefly comment, because it has also already been introduced, is the solution of the time-dependent Kohn-Sham equations on the framework of the time-dependent density functional theory. So you solve these equations for the Kohn-Sham orbitals, where you have first the kinetic part, and then this Kohn-Sham potential, which includes the interaction with the ions, with the laser, and also these two other potentials, which describe in one case this density-dependent Hartree potential, which describe Coulomb interaction like with the gas of the gas of electrons, and then this exchange correlation. Spin density dependent exchange correlation potential.
All right, so why would you choose one method instead of the other? So for example, what are the advantages of PDDFT, for example? So as Francisco just said, of course, it's very good because it allows you to treat a system of, in principle, interacting electrons, well, in terms of an equivalent system where the electrons are not interacting, and it's much simpler to solve, and therefore provided, of course, that you have determined a proper potential exchange correlation potential. So of course this is easily scalable, and so it's particularly suitable if you want to treat larger systems, but it's also being used actually to treat smaller systems, but where you might want to selectively control the position of the atoms without having to fit all your parameters as you would have to if you were to solve the semiconductor Bloch equations, for example. And these are two examples that I'd like to mention. One is from Dieter Bauer. In this case, as he also mentioned before, in this case, he was looking at two different phases in a linear chain where the spacing between the ions changes, right? And then So you see here, these two are closer than these two here. And then depending on what you start with, you might have these topologically protected edge states. And if you have them, then what was observed in this paper is that you have a significant increase in the HAG signal. And this was simulated with DDDFT. But also in this case, if you include doping, for example, right? So if you want to selectively modify the type of ion in your linear chain of ions, or in this case, if you look at your donor dope system, then you will have these additional states, especially this one, this occupied state here, which is particularly close to the conduction band, and therefore can lead to a significant increase. You see the red line here of your HA signal as well, as shown in this paper here from the group of Laspo and Messen. So these are cases where using TDDFT is advantageous. Of course, it has limitations. Determining this exact, a suitable exchange correlation potential can be challenging. You need to have determined that first. And this can be particularly hard, especially if you want to deal with core states, or if you want to include excitonic effects, as Simon Jensen has mentioned before. And this becomes also challenging. Well, you must have determine a suitable exchange correlation potential if you want to suitably describe Rabi oscillations as well. And so this can be challenging as well. Now, on the other hand, if you look at the semiconductor block equations, in this case, you have this set of equations. It does not require the determination of an exchange correlation potential, but it requires fitting all these parameters, right? All the dipole couplings and the energies. And so you must know and you must have fitted all these parameters, which for larger systems can become tedious. You might not be able to have fitted them all. So of course there are pros and cons of the two methods, and depending on the system you look at, you might prefer one to the other. I personally use a combination of both. It depends. We will see at the end what you prefer, right? As you said in the talk.
Okay, so all these methods apply for numerics, but now I want to talk about analytics. And in analytics, what we want to do, well as in numerics, is to solve a Schrödinger equation. And in order to do so, we project with respect to some basis. And in principle, when in terms of the physical observables, there should be, there must be no difference between the results that we get with different bases. And okay, in our case, our observable will be the high harmonic generation spectrum, which is given, as we have seen in all of the talks, as a sum of the interband and intraband currents, but I will focus mostly on the interband contribution. And as we see, we will talk about Bannier and block bases. And as we can see in this plot here, there is no practical difference between the harmonics generated with one basis or the other, as expected. There is a small shift here, but this is just to not make the plots overlap. So in principle, one may think that this debate between the bases is sort of irrelevant, but actually I think it's not, because as I said, it can provide very different insights about the underlying processes. And in particular, when we talk about such as different bases, like the block and Bannier bases. So to me, one of the main disadvantages about the block basis is that it is delocalized in space while being completely localized in reciprocal space. And on the other hand, Bannier basis is completely localized in space while being delocalized in space. This is the main advantage that I found for Bannier basis. And the reason for this is that because it provides an atomistic picture of the high harmonic generation processes in solids. So on one hand, this allows us to look at the difference between the process in solids and in atoms, but also we can use the knowledge that we have from atoms in order to map it somehow to solids. And regarding the underlying physical processes, this is something that can be seen already at the level of the interband current. So in the block basis, so here, what we have is basically a sum over a given, over a set of probability amplitudes that tell us that the electron starts, it gets promoted to the conduction band at time t prime, and it returns to the valence band at time t with crystal momentum k. But nothing is said about what happens in the real space. And now if we go to the Bannier basis, what we have is a sum, but in this case is given over different sides, J and L, telling us that the electron appears in the conduction band at side L, and then it returns when it's found at side J. And in principle, side J and L, they can be different. And this highlights something very important in solids, is that this process is a delocalized process. And this is even further highlighted if we apply the saddle point approximation and look at the one given the classical trajectory. This was mentioned also in the morning. And we have that, unlike atoms, this term is different from zero, which suggests, I mean, the localized nature of the harmonic generation in solids. And I think this is something that can be used in order to map the harmonic generation in atoms to solids, because, for example, in atoms, when we perform the typical calculations with a single particle, what we get in the harmonic spectrum is something that is not well resolved. I mean, the harmonic peaks are not well resolved. And this typically is something that happens because, I mean, we have to introduce macroscopic effects. And these macroscopic effects make the long trajectories of the electron, because some extra phases that appear, to interfere destructively. And this leads to the well-resolved harmonics. I mean, for example, in this paper, what was done is something similar to, I mean, despite what's happening in atoms, they consider that the long trajectories, in the sense that L and J are very far away, they accumulate an extra phase and they interfere destructively, and this allows us to get well-resolved harmonic spectra, but without the need of introducing very long dephasing times, which, as we will see, is one of the main problems, or we have heard as well, is one of the main problems in theory. Also, regarding the classical trajectories in the saddle point equations for the block basis, what they tell us is that the center of the electron and whole wave packet have to spatially overlap. But of course, I mean, further research has shown that when taking into account some extra effects, such as the so-called electron hole pair recollision at energy that we have seen before, these trajectories get very much affected. So we get, as we will see, this is for the same material in both plots, the same conditions, but with and without taking into account these effects. On the other hand, I mean, I have presented sort of Vanier and Bloch as being in a sort of debate or in a duel, but actually they can collaborate together. And this was very nicely presented in this paper by Sika et al., where basically what they did is to study valence band with Vanier states and conduction band with Bloch states, and this resembles very much the picture that we have in atoms. So initially the electron is localized in the ground state, then it goes to the continuum, which in this case is the conduction band. Here it can get delocalized, but then afterwards it can recombine basically anywhere in the solid. So regarding which one to use, I think, of course, this is a matter of taste, it's a matter of interpretation. In my case, I prefer Vanier-based methods because I started working in high harmonic generation in atoms and then I started as well with solids. So this provides me a better picture. But as well, I mean, and this is something that we want to discuss with you if you have any preference. Also, one can select its preference depending on the practical uses. So for example, now this debate can also be extended to the numerical realm. But now we talk about a truel because now the laser gauge plays a fundamental role. And in this case, I don't have any specific preference, but I think one should choose the method that best suits the material or the observables they want to look at. So imagine that we blindly pick the block basis in the velocity gauge. The first thing that we will see is that the equations that we get are decoupled in K, which is very nice from a numerical point of view because it allows to introduce all these polarization processes that use the numerics. But however, if we want a more detailed carbon decomposition, then what we can do is to move to the length gauge, where now the main problem is this K-dependent phase that we heard about in the talk this morning, which in numerics is typically random and leads to very huge problems when we compute the transition dipole matrix elements between the transition dipole matrix elements. And this is a problem that only appears in the length gauge. If we work in the velocity gauge, I mean, it doesn't matter how we do the numerics, we get the correct harmonic spectrum. And in order to fix this, what we have to do is to fix these gates and therefore we can solve somehow the problem. Another problem that there could be is that the number of K points that we need in order to perform the numerics. This can become very huge, especially in situations like this one, where, well, I don't know if you can see. Well, okay. What it happens is that in some cases, the transition dipole matrix elements in K space may become very big, and this requires a lot of K points in order to have convergence. What one can do here is to move to the Vanier basis because now the transition dipole matrix elements become smoother and decay exponentially with distance. And therefore, one can sort of avoid this problem. But still, we have the problem of the K-dependent phase, which might make us go to the block basis in the velocity gauge. Another way of avoiding the problem is to use combined methods as presented in this paper over here. where they basically combine density fractional theory methods with semiconducting block equation.
Okay. So related to ATAS, instead, what are the things that are specific to ATAS that you need to take into account when you want to compute the signal? So first of all, let me remind you what the signal is from when you want to compute it, right? So as I said, in ATAS, you look at the transmitted propulse after it has passed through the medium. So you are basically looking at the spectrum here of the pulse in output here, which is basically the sum of whatever pulse went in input plus the field that was generated during the interaction with the medium, right? And the generated field is related to the dipole response of the medium itself. Basically, the input field will induce a dipole, an oscillating dipole that will lead to the generation of a field. And therefore, the field in output is, and the spectrum, basically, of the field in output will be the spectrum of the field in input, the incoming pulse, plus this interference term, plus this additional term that is weak, so I'm neglecting it. So it's basically this interference term. It's the interference between the incoming pulse and this generated field that you know once you know the dipole response of your medium. So this is basically the quantity that you need to compute. The dipole response, the XUV or X-ray dipole response involving these inner core states, right? These valence band 1, for example, shown here, right? This is for once you know this dipole response, then you can calculate the absorption spectrum, and this is, for example, what you would observe here in atomic units. Now, what are the computational aspects that you need to take into account that are specific of ATAS? Well, of course, you need to include the core states that are accessed by the XUV or X-ray propulse, and therefore you need some suitable techniques in order to compute the energies of these localized states, and you also need to know, the dephasing times that are involved due, for example, to a jet decay. Challenges specific to TDDFT are, of course, you need to determine some suitable exchange correlation potentials that now don't only describe properly the delocalized valence states, but at the same time, also the localized core states. And so, for example, strategies that are being studied, that are being developed, involve some suitable long and short range corrected exchange correlation potentials. But this is really an ongoing field of research, determining suitable exchange correlation potentials that can describe simultaneously both.
So now we'll try to kind of talk about a few of the topics that in our field has been a bit caused some discrepancies between maybe theory and experiments predictions. So firstly, it's more of a philosophical question to you guys. Do you think, are you more on the theory is always right and we have to focus on discovering new physics, or maybe on bridging the gap between the experiments? Oh, sorry, I switched the question now. Okay, sorry, now. Or are you more on the fence in between wanting to bridge the gap between theory and experiments? So I will be on the side of experiments represent the real world, and I'll take a few seconds to maybe complain about some of the theoretical stuff. So as you see here, and I chose probably a very bad paper because Francisco actually is on this paper and he modeled that work. But as you see, for even small complex systems like here, just some doping from chromium of MgO, the group here did cutoff predictions for MgO and doped MgO, and even with insignificant amount of doping, they saw this shift to higher cutoffs equal to about 1.8 eV. That agreed with the shift of the band gap that they measured experimentally. However, in this theory itself, it was very hard to actually reproduce it. So sometimes, even though in all the theoretical papers that they like to tell us that we will see a nice separate peaks with a beautiful plateau with a clear cutoff, in reality, obviously, depending on the sample and depending on the experimental system, we see something very different. So we will talk about a few of those discrepancies now and try to discuss maybe where they're coming from.
Okay, and it is a beautiful paper. And yeah, so and then the next question. So regarding this discrepancies that sometimes are found between the numerical calculations or theoretical calculations and experimental results. Yeah, we want to know, in your opinion, which might be the main source of these discrepancies. I think that there's not a single one, but perhaps there's one which is more concerning for you. So let me first start talking about the phasing and what drives my interest towards the phasing. So yeah, there are some reading the literature, you find some theoretical and experimental works or comparisons between them, which lie in three categories, which I find relevant to this talk. So, for instance, complex experimental setup, like this work with impurities, right? So where the target is already difficult to model theoretically, or experiments where the laser is has a complicated shape, or it's tailor-made. And then when you have so many additional ingredients which make the calculation difficult, perhaps not having like a great agreement between theory and experiment can be acceptable, right, or expected at least. Then you have other set of experiments which, even with a simple model, they can describe really complex experimental conditions. And yeah, perhaps this is surprises, but not surprising, but somehow positive or lucky, right? But and perhaps that can be a signal that perhaps the effect is so strong that even with a simple model you can describe those experiments, right? But then you have a third set of experiments which perhaps are performed under more like standard conditions, or are experiments which are well known. But even when you try to model them with more like complex methods, which try to include as many microscopic ingredients as possible, do not reach like a good agreement between a theory and experiment. And so regarding this, for instance, we can discuss, for instance, here on the right, we see the experiment, the results of Shambhu, of his foundational experiment, which is to our field, right, of Attoscience of Solids. And so in this experiment, we see a spectrum which is composed of bright odd harmonics, right, as you in principle expect, because of the laser polarization and because of the inversion symmetry of the solid along the polarization direction. But nevertheless, on the left, we see the first more complete description of this experiment, or at least the most paradigmatic theoretical modeling of this experiment. And as you see on the top, we see the results of the semiconductor Bloch equations with an infinite dephasing time, which, as I mentioned, is equivalent to solving the TDC. And even if you sum all the contributions along, not all, but in this paper there were like hundreds of contributions along the Riemann zone. They modeled the band structure with the results from DFT, which were already well known for zinc oxide, and also they used the correct transition dipole moments. But even though you include all those ingredients, then you have even not quantitative difference, but you have qualitative differences with what you might expect. So if you add no dephasing time, you do not find the odd harmonics which are measured experimentally. But on the other hand, when you include on the semiconductor block equation this effect, the phasing effects, you achieve good agreement, so the peaks look sharper and are at the right position at the at odd positions in the spectrum. But one have to be careful, or you have to know that by including this the phasing times, one is not only changing the spectrum, but also the dependence of the spectrum regarding the as a function of the laser parameters. So, for instance, on the top we see the interband part of the current, and as you see, the interband current with the infinite dephasing time and with short dephasing times is different. So that also has to be considered when using this the semiconductor block equations. And so what's the meaning of this dephasing time? So mathematically it appears on the as I showed before on this interband matrix element, right? And it generates a decay because of this form, right? And then, as I mentioned, the most relevant to HAC solids is this T2, because it's the other relaxation time is some orders of magnitude longer. So in the end, numerically, it doesn't make much difference. And it describes the decay of quantum coherencies, and it's used, even though it can be dealt with more like analytically, but it's usually used in a phenomenological way and tries to account for electron scattering. It could also take other effects into account, but usually it's believed that the main contribution comes from electron scattering, which is not included in the semiconductor block equations. And the typical values which are used in calculations are on the orders from 1 to 5 femtoseconds. But on the other hand, experimentally, that's not like fully justified, because usually the dephasing times that at least were measured in the 90s are on the order of above 10 femtoseconds. And that makes us think of the physical meaning or the physical relevance in HAC solids of these dephasing times. And for instance, we can cite some interesting points of view. For instance, in the paper from Bampa from 2014 that I commented before, they mentioned that perhaps it's because these dephasing times that are higher than 10 femtoseconds were measured under different experimental conditions how we use it in HAC solids, right? So this because of the intensities, the electrons in the other experiments where this T2 was determined, the electron was only sitting like at the gamma point, while in HAC solids, because of the intensities, the electron explored the whole region zone, and that might lead to shorter dephasing times because of the higher bandgap energies. And also another interesting observation that I found on the literature is that like in reverse the plot, the group of Jacob Borner proposed that perhaps the HAC solids could be used as a technique for measuring these dephasing times under these more extreme experimental conditions. But still, one question remains open, is that why, if this dephasing time comes from electron scattering, why even when we use TDFT, we do not get this clear harmonic spectrum? So this discrepancy between the calculated spectrum, also this absence of the clear defined harmonics is also present in TDFT. So that make us wonder, okay, it's perhaps that we have not found the correct exchange correlation potential, or perhaps there might be other additional macroscopic effects which might be responsible for those disagreements, right?
So I found this discussion of the phasing a very interesting kind of case study of how the theory and experiments behave, because sometimes when, as a starting PhD student, it seemed like there was a lot of infighting between the theorists about what it is. But obviously, as Shambhu already showed, the experimental see the harmonics being harmonic from the beginning. So we kind of cannot just play around with that time as much. And experimentally, we can try to measure it in different ways, but it is a bit difficult. And I think this kind of discussion highlights the need of other measurables that should be coming out of this different theories that are testing something. So here I'm presenting the figure from this paper from Wang from this year, where they saw this harmonics, and by using a experimentalist group, by using a kind of toy model, was trying to play around with how the dephasing time will actually influence the divergence of harmonics. And I don't know if theorists would really want for experimentalists to step in here and try to come up with our own observables, but maybe that's kind of the cry for help in need of some measurables.
Right. Well, of course, dephasing times play a important role also in Attos. And here you have the additional dephasing due to the core states that, of course, you need to take into account when modeling. But then also, you know, the other dephasing processes that we mentioned before, of course, you can also observe them with Attos. Attos remains a pump probe technique. And so far, I've mostly thought about Attos as a technique to look at what happens in the presence of the intense pulse, because, well, that's the region that they're interested in HAG as well. But you can use Attos as a pump probe technique to look at what happens afterwards, right? And also to look at the dynamics of your system, of your solid, are just initiated by the intense pump pulse. And this is, for example, these are two examples. In this case, the real advantage of Attos is, as I mentioned earlier, the fact that you're using this very short and therefore very broadband pulse that allows you to look at the dynamics in a very broad set of energy states, a very broad set of bands, as shown, for example, in this paper here. And of course, by scanning the time delays, you can look at how the charges will move in these different bands. You can also observe coupled phonon electron dynamics from Attos and extract lifetimes of carriers in different conduction bands. Just to say that, of course, in Attos, you need to take into account these dephasing processes as well. And also not only in the presence of the intense pulse, but also afterwards.
So I also wanted to mention some other discrepancies that I noticed and I think are really important from the experimental point of view. So propagation effect is, I think, the big elephant in the room here. And here, a very good paper by some notable authors are presented, where they did an interferometer from the high harmonic generation by basically spatially separating two sources of HHG, and they were looking at the shift of those fringes here to kind of look at the dipole phase shift between harmonics when they change the intensity between the two pulses. And you can see here that depending on geometry, this phase shift fringe shift was very different. Even the direction of the shift, not just the magnitude, was different, which can suggest some very strong propagation effects, especially when we're looking in transmission. And also, as we talked a little about before, this experiment also showed really well how important it is to look at kind of different solids, and to remember that the solids are not in a strong field approximation. We can just forget about what we're generating the harmonics with, because the sample actually was really important as well if it comes to the measurement. And even for the simplest case of harmonics, when you just put some solid in a sample, when you're trying to pump it a bit too hard, you get those beautiful fringes. So those are some of my own results that I'm trying to kind of understand. But you get those beautiful fringes out of your harmonics when you look at the spatial divergence versus the energy of the harmonic. And this is also a propagation effect that is very dependent on the thickness and the intensity of the driving laser. And this is also shows you the importance of kind of different types of propagation, because this is only visible in the far field. So look at taking into account what your spectrometer is imaging and how that will affect your observables is also something that we should try to kind of look into.
Okay, well, from the as I mentioned before, yeah, there might be some additional effects which perhaps not replace the phasing, but perhaps are coexisting with the phasing for explaining these discrepancies between theory and experiment. So, for instance, one of those effects might be the propagation of the laser through the material. So, for instance, in this work from Ploss et al., they considered also the propagation effects in two ways. So they solved in a really computationally intensive calculation the solution of the Maxwell-Bloch equations, and also they considered the shape, the transversal Gaussian shape of the beam, right? The intensity dependence of the beam in the focus. The spatial dependence of the intensity of the beam on the focus, and as you see on this left on the bottom left figure, when they consider these propagation effects and also the effect of the finite size of the laser in the transversal plane. They already start observing well-defined harmonics, and this agreement is even better when they consider the phasing times, which is in this bottom right figure. So they had to use only the phasing times on the order of 10 femtoseconds, which is more experimentally reasonable, as I mentioned. So this can be a good candidate, but on the other hand, there have been measurements which were not performed specifically for looking to this, but experimentally experiments performed in transmission and reflection. And in fact, instead of seeing like a sharpening of the harmonics because of the transmission of the in transmission measurements, you find like a more broader spectrum. So at least that cannot be like the ultimate answer, or more ingredients need to be considered. And then we have yet another candidate, which is the propagation, but outside the material. So like a near versus far field shape of the harmonics. And in this case, they consider two ingredients. So they consider also the finite size of the laser, of the laser spot, and also they consider the propagation of the laser, so the far field observable, and then the refocusing of the laser to the detector. And by doing that calculation, that type of calculation, they also found more well-defined harmonics. So as we see, we have many candidates for this discrepancy between theory and experiment, and well, I think one might consider, okay, we need to calculate the whole propagation through all the optical elements for achieving a good theoretical and experimental agreement, or what the solution for this might be.
maybe I'll just skip through some stuff to go to the results of the question. The only last thing I would want to mention is something that I think we have to talk about as an open debate, is all the experimentalists just claiming we never burn a sample, but in both of the ATAS and high harmonics, that's just a very real issue that I think we maybe want to discuss a bit more. So let's maybe look at the results of our polls and of what people kind of answered to the questions. And now we would want to also answer the kind of open the discussion here. So that's our first question. I feel outnumbered, but and here,
Now I feel outnumbered. Okay, well, no, but there's also the both. Okay, good.
Yeah, so you can see here that even though most of us are working in high harmonic generation, we keep talking about for electron dynamics. I don't know if Stefano would want to kind of comment on that.
Also those working with HAG, so
So anyone has?
so anyone has
Some points you want to discuss?
I don't work on solids, but a question one would ask, because I don't work on solids, but a question I would ask is for you, what is the biggest elephant in the room? Because you proposed a lot of aspects, but for someone who is looking from the outside, it's not clear, okay, what is something that we really need to talk about and why?
You can skip to some few answers. We did ask that question at some point. I think it does agree with me that for from an experimentalist perspective, the propagation effects are kind of an important thing that we would want to talk about. Obviously, as experimentalists, we can try to move away from considering it by looking at very thin materials or looking at reflection geometry, but whether we can completely ignore those things or whether we're not gonna just introduce other challenges that as an we will have to look at is something that I think is very interesting.
what are the other?
Yeah.
So
Anybody has a comment or a question? Yes, Shambhu.
I just want to add, it's not just only the propagation of the light, right? Maybe also the propagation of the electron inside the material is one of the big lessons.
Did you think about the material itself? Is it clean at the surface? Is the surface important?
Yeah, that's something.
It's very quick that you absorb, you oxidize your surface or water or many layers.
Yes, especially when
change many things very quickly.
Yes, yeah, especially when working with very thin films or of materials, they do change quite a lot with time, which I think that the topological states show that just oxidizing it with air change the yield of the harmonics quite quickly.
So we want to discuss more. Do we want to discuss, is experiment the ultimate truth? Does theory need to improve? Does experiment need to improve? Do we want to meet halfway at least?
so one of the questions was, what is in your opinion the main challenge if we want to make these techniques real,
So
analytical
we
techniques?
can say this, so we can do this. So maybe can somebody comment, or does somebody want to discuss how should we improve the theory and why? Or maybe how should we improve the experiments and why?
Yeah, if you want, if you don't want to speak, there is an open-ended question. You can type some of your answers at the end if you don't want to kind of answer. But I think the big question here is that Stefano wanted to ask is
on the screen there's the
Yeah, do we want to talk about this?
yeah
I like that answer, so I don't think we should question it.
yeah, so for instance, I think
This is partly a plug for tomorrow afternoon's panel, but it strikes me, and I say this as somebody who's a single atom theorist, but it strikes me that experiment has benefited over a number of years by, it's my impression at least, that there's a class of professional technician, right? So you professionalize a lot of the work on the technologies, the detectors, all of that stuff. And that same professionalization hasn't happened in theory, where people who are scientists are trying to do high performance computing or code development or whatever. And tomorrow afternoon's panel is about this very issue and how in the UK this has been kind of identified as a real gap. And how if we can professionalize the kind of software development aspects of theory, this might actually help to accelerate and bridge some of these gaps. It's just an idea and also an encouragement to come to tomorrow afternoon.
Yeah, for
So
instance,
is there anybody who wants to comment on it? Do we need to professionalize the theory aspects?
yeah, so regarding this this answer, yeah, I find it interesting. So yeah, so I think theory has a predictive power, but also allow us to understand the processes behind what the experimental finding, and that also later allow us to make better further predictions, right? We cannot like stay in a purely like a phenomenological way of workflow where we say, okay, we changed this and we got excellent result. We also need to know why, and yeah. So as a theorist, one might want to introduce propagation and full electron correlation, but yeah, one has to put the boundary at some point, or need to say, okay, what of these processes I can model in a more simple way, because I cannot do the full calculation, right? So in propagation, perhaps, okay, I can just consider the propagation of the driver laser, perhaps with the refractive index, and say, okay, approximately this will be the intensity of the laser at the last layer, and then this is the intensity of the laser of the first layer. But sometimes you do that simple calculation and you don't get such a what you would expect, right? And then that might make you think, oh, okay, I need to further consider reabsorption. But already sometimes the microscopic calculations is already too heavy to, on top of that, make the full propagation, right? And
maybe also as a response to you, I just wanted to say there's still SAT PhD students working on everything from getting the lasers up and running every day to getting high harmonics and the detection and MCP working. So I think, yes, I agree that going to a beam time when you have a linked scientist doing loads of the stuff is very, very good. But I think quite a lot of the high harmonic generation papers are still done in kind of more of a home facilities in dark rooms.
Wants to say something in the audience? Do you have any more comments about this? Or any other questions that were raised by the panelists? So we are all happy, theory is perfect. Maybe so are experiments.
so we'll see the next one, right? So can we see the next one?
Yeah, we just saw that.
Okay.
Perfect. So that's just for you guys. If you think that you wanted to vote on any kind of other discrepancies that we didn't mention, maybe before we go up to the coffee break, you can leave that open and we can have some more discussions.
Is there anything you want to add? Anybody?
Well, I think Bravek today said he wanted to include temperature effects also, right? So it's like he was not completely happy with this phenomenological dephasing that
So
he
effects, which includes, I suppose, the nuclear effects. Anything else? Anybody has a wish list? Surely you have a wish list. Surely, especially the experimentalists have a big wish list of things they wish theory could do.
Well, the TDDFT specialists on the audience, what's their opinion on the dephasing time?
Yes, so what about?
Do you have an opinion at all, or?
Including decoherence and dephasing effects in TDDFT, do you think we can do that?
So first of all, like I think it's like active research to add phenomenological dephasing to TDDFT. So it's kind of, there's some papers talking about it, but I think the main term is electron phonon coupling, basically. So it's not really the electron scattering so much that's an issue, but the presence of phonons actually is temperature. Like this is the biggest, to me, this probably is one of the biggest. It's hard to pinpoint because there's so many things that theory just doesn't get. I mean, we sometimes forget how many things we neglect, but we neglect so much. But for the dephasing, like the just temperature and phonons, and you can add them to TDT, to TDC, to tight binding. So these you can add. There are quite a few papers on this, and this has been shown to clean up harmonics, and also to give like correct time scales for intervalley scattering. You know, so this you can add.
Yeah, and I think in experiments it's quite important. Temperature is quite important because when you shine a laser with a solid, it does get hot over time. And I think especially where in our group they were doing probe experiments on solids, like one of the papers there was on a P3HD when they were trying to probe the dynamics. They had a big problem with just melting off the sample, and they had to design some engineering copper wire cooling stuff just to be able to pump it kind of to significant enough effect. So I think in theory probably that's something that we should also.
So there's temperature and temperatures.
So I have a question for Shambhu. So have you performed measurements as a function of theory or as of a temperature, and how well documented the temperature at which the experimentalist is offered in papers? Do you find that it's well stated so that it can be analyzed? Or?
I think so far what people have explored, these are experiments on relatively large band gap material systems, where the temperature, as the laser photon energy is much smaller than the band gap. So you don't, in principle, you don't actually put a lot of energy in the system, right? So in that sense, there is not so much the temperature dependence, what would influence the generation, significantly. But what I would expect from theory colleagues is to calculate the response of some interesting electronic states like superconducting states, where the temperature actually matters a lot, right? Mm-hmm. For example, a specific example problem is, if we can calculate the harmonic signal from a Moiré pattern that is superconducting, where the temperature really matters, right? You need to get right, temperature. So, it would be really nice to have some predictions of, how the harmonic spectrum would be different when you go from, from such phase transitions, such as these topological phase transitions in Moiré systems. And so
Another one?
Oh,
Yes.
I just want to make one point. I think it's great that we have a discussion, but don't forget that we have a vote to take.
So one last one? Okay, the last one.
I'm not doing solid HAG, but I wish to congratulate both the experimentalist and theory working on it. I think in the past, at the beginning, obviously, experiment drive the science, but I feel that recently also theory gives new concepts that drive the work of experimentalists. And from my point of view, this is really, it's great that theory drive experiments and the otherwise versa. So both aspects doing good job.
Okay. So maybe we close the session at this, and let's thank our panelists.